In this video, we provide an introduction to liquids and solids. Right, let's review the three states of matter that we're interested in chemistry. You have gases, liquids, and solids. So let's fill three containers that are identical with a gas, a liquid, and a solid of the same substance. What will happen in the gas is that the entities of the gas, the particles or molecules that are making up the gas, occupy the entirety of the volume of the container and conform to the shape of the container. Okay, so this is what we call a gas. In a liquid, a way to define it is that in the liquid, the molecules will conform to the shape of the container, but will not occupy the entirety of the volume. And in a solid, you actually have that those molecules, or that state of matter, neither conforms to the shape of the container nor occupies the volume. That is the solid. Okay, at a more fundamental level, something that is very important about gases, and that is different from solids and liquids, is that in gases under normal conditions, so 1 atmosphere of pressure or so, the average distance between the gas particles is really far away, and we can assume safely that those gas particles do not interact. However, in a liquid and a solid, those gas particles are actually very close to each other, or those molecules of the species are very close to each other, and they're going to interact for sure, much as they will in a solid. All right, so that is the main difference between liquids and solids, and that is that the particles or the entities that are making up the liquid and the solid interact with each other relatively strongly, but in the gas there's a complete absence of those interactions. Okay? A way to quantify the type of interactions that you have in a solid and in a liquid, and the absence of those in a gas, would be to look at phase transitions between the three states of matter. Okay, so we can look at the vaporization of, for example, water. Okay, at 1 atmosphere of pressure. Okay, this takes place at about 100 Celsius, or 100 Celsius exactly if you're working at 1 atmosphere of pressure. Okay, we're going to turn this liquid into the gas at the same conditions, 1 atmosphere and 100 Celsius. And when we measure the enthalpy, the molar enthalpy change for this for this phase transition, that happens to have a value of 40.7 kilojoules per mole. Right. Something important is that in this phase transition, we're actually not breaking any covalent bonds. The only thing that we're doing is breaking or separating the molecules, right? So this is a really good measure of the interactions of molecules in the liquid to a situation in which those molecules do not interact, right? So that it gives you a really good measure of how strong those interactions are between molecules in the liquid phase. Now, notice that 40.7 kJ per mole is much lower than a typical covalent bond, right? So for example, the OH bond in water would be about 480 kJ per mole. Okay, so while these interactions are not as strong as what you have in a covalent bond where you're sharing electrons, nonetheless, they're fairly strong. They're about 10% of what you have in a typical covalent bond. Now, this is the measure of the interactions in the liquid that are broken off as you go into the gas. But then you can try to do the same thing from the solid to the liquid. So this will be melting or fusion. And then that will give you an idea of the difference in the strength between the interactions in the solid and in the liquid. Okay, so that will be water, go to the liquid, 1 atmosphere, and now 0 Celsius. And this is what we call fusion, and the enthalpy of fusion under these conditions, molar, this is standard, that will be about 6.10 kilojoules per mole. Okay, so clearly, breaking interactions in the solid and making that a liquid actually takes much less energy than breaking interactions in the liquid and making that a gas. And this is fairly easy to understand, right? So notice that what we're doing is trying to break off the interactions in the solid and generate a liquid, but notice that not all of the interactions are broken completely. Some of them are retained in the liquid, and that is what the reason that you actually have that low enthalpy of phase transition compared to what you have here in the liquid and the gas. As a matter of fact, for water, we actually have characterized the liquid phase and the solid phase quite well, and we can talk about interactions between neighboring water molecules. We will actually study in next videos what a hydrogen bond is, and it turns out that in regular ice, each water molecule is interacting with 4 hydrogen bonds to 4 neighboring water molecules. Now, when you actually turn that ice into the liquid, those water molecules are still forming hydrogen bonds with neighboring water molecules in the liquid. But on average, you have about 3.4 hydrogen bonds as opposed to just 4, or as opposed to 4, which is what happens in the solid. Right? So clearly, because you're breaking some of the interactions, but not many of them, right? That doesn't take as much energy than when you're breaking all of the interactions that you have in the liquid to go into the gas when there's no interactions at all. Okay, finally, we can wrap this video on the separation between the gas phase and the liquid and solid by saying that the densities are also quite different. Okay, under regular conditions of temperature and pressure, so about ambient conditions or so, for water, we actually have that the liquid and the solid, the densities are fairly similar, right? There will be about 10% or so different from, say, liquid water at 25 Celsius to ice at 0 Celsius. But if you were to measure the density of water vapor under low temperature, you would actually find that the density is about 1,000 times lower. Okay, so 10% difference in density between these two phases, 1,000 times lower density, which again means that essentially there's empty room between those gas particles. Right, so in this video we actually have studied the main separations between the gas phase and the liquid and solid phases. As it turns out, the main difference is that in the gas phase you don't have interactions with neighboring particles, but in the liquid and the solid phase you have strong non-covalent interactions between those molecules or entities of the liquid and the solid. In the next video then we're going to try to study a little bit how those interactions, what type of interactions can you have in a solid and in a liquid phase.